Hello everyone, this is Jay from BTYT Tech Library. Today we are going to do ethical hacking on HackTheBox Nexus machine for educational purposes. This box allows us to practice a full attack chain. First, we discover a Git repository by scanning the target's vhost. Then we dig into the history of configuration files to find hard-coded credentials. Using these credentials, we log into another service on the target called crin and exploit the file upload vulnerability CVE 2026-38526 to gain initial access to the server. Once inside, we exploit a path vulnerability in a systemd scheduler script that syncs gitea templates, allowing us to upload an unauthenticated persistence file and escalate our privileges to root. However, during this process, I discovered another gitea vulnerability CVE 2026-60004, which allows for a much more direct route to privesc. Because of this, we are going to create an alternate arc halfway through. We will walk through both method and study the core concepts behind them together. Let's hack this box. First, let's run the Rust scan. Let's go ahead and add the nexus.htb address we found in the scan results to our /etc/hosts file. While running another scan in the background, let's go visit the web page. Alright, we've landed on a page called Nexus Energy Authority. Let's take a quick look around the site. Most of the links and buttons seems to be anchored with a sharp mark, which makes me suspect this might be a single-page application. Oh, look at that! There's a button for an operations specialist job posting. Let's click on it, shall we? In this modal window that popped up, we can harvest the emails for both the recruitment team and the hiring manager. You know, job posting like this are actually a fantastic OSINT and reconnaissance window because they often give away exactly what technology stack a company is running under the hood. For now, let's run a directory scan to see if there are any hidden or unknown paths hidden away. While the scan is running, why don't we take a peek at the page source as well? Well, nothing really interesting stands out here. And as expected, the scan results show absolutely nothing except for the index.html page. But hey, no need to get discouraged just yet. Let's go ahead and scan for vhost, shall we? I'm using Cobust here, but feel free to use whatever tool fits your preference, whether that's PhenixBuster, GoBuster, or FOF. Nice! git.nexus.htb and billing.nexus.htb have been detected. Let's not forget to add these addresses to our /etc/host file as well. First, let's head over to git.nexus.htb to see if we can harvest some useful information from the source repository. Ah, it's a gitea page. And they are running version 1.26.0. Let's take a look at the sign-in section on the main landing page. Looks like user registration for signing up is disabled. It seems like getting it won't be easy unless we can somehow obtain valid gitea credentials. In the meantime, let's do a quick check to see if there are any known vulnerabilities for this specific version. Alright, looking at the summary, it says gitea's diff patch endpoint can be abused to install and execute a git hook from repository controlled contents. Long story short, if an attacker has ordinary write access to a repository, they can leverage this flaw to execute arbitrary shell commands as the gitea OS user. On a default setup with open registration, an unauthenticated visitor could just sign up, create a repo, and get that write access instantly. For now, let's try to exploit this using the public POC provided at the bottom of the page. But wait, as I'm typing out this command, I'm starting to get a feeling that this time it's not going to work out because we don't have any user credentials for the target gitea instance. And yep, just expected, it's blocked by authentication and doesn't go through. Looking around, there aren't any other vulnerabilities that look immediately exploitable in our current situation either. Alright, so let's move on and take a look at the billing page instead, shall we? Okay, we've landed on a login page built with Crane CRM. And the Crane version is... well, it's not listed here. If you look at the bottom, there's a debug bar showing the Laravel and PHP versions, but unfortunately, still no sign of Crane version. I wonder if there are any default credentials we could try. Shall we? To be completely honest, I panicked a bit and got stuck here for quite a while. It took me some time to realize that I hadn't even checked the Explorer section on the target's Git page yet. Let's go check it out together. We can see a crane-docker-setup repository created by the user admin. Let's take a peek inside the .env file, shall we? Right, we can see that they followed best practices by not leaving hard-coded credentials right here on GitHub. But as penetration testers, we must never underestimate the power of the Git history section. And voila! Look at what we have here. We can definitely use this. You know what they say, hackers don't break in, they log in. Wait, oh my! Wow, okay, we are safe. Now that we are inside the dashboard, we can finally confirm that the Crane CRM version is 2.2.0. Alright, let's follow this proof of concept and see if we can get our hands dirty with some penetration testing. As you can see, this is a textbook example of a malicious file upload attack caused by a complete lack of file extension validation. Okay, now we are in. Let's do a quick check on some common Linux privesc vectors, shall we? Nothing really useful stands out at first glance. Right, what's next? Let's check if there are any services or scripts running on a regular schedule. First, let's look at systemctl. When you run systemctl list-units, you are looking at the big picture. It shows everything currently loaded in your system's memory, services, sockets, and devices. But since we only care about scheduled tasks that we might abuse for privesc, we'll use systemctl list-timers. This filters the noise and shows us exactly when a task will run next, how much time is left, and what service it triggers. It's like a dedicated dashboard for the target server's automated jobs. Now you might ask, wait, why not just check crontab? Well, crontab is the absolute classic. It's incredibly simple. You open a file, write a single line, and boom, your script runs every midnight. It's portable, fast, and works on almost any Linux server. For quick, independent automation, crontab is still a great choice. However, modern system administrators and DevOps engineers prefer reliability and control. That's why you will see systemd timers shining in modern environments like this box. Unlike crontab, which only goes down to the minute, systemd timers can trigger tasks down to the exact second. Even cooler, they can set relative times, like run this task exactly 10 minutes after the server boots up. Plus, because it integrates perfectly with systemd, debugging for admins is a breeze. They can check exact logs using journalctl and even limit how much CPU or memory a task can use. No more hidden failing cron job. So here's the golden rule you should keep in mind. System administrators use crontab for simple, quick, one-line automation. But for production-grade architecture where they need deep logging, precise timing, and resource control, systemd timers are the way to go. And for us as attackers, knowing how to enumerate these timers is exactly how we find hidden gems to exploit. Let's see what timers are running here. Inside the systemd timers, we can spot a timer called gitea template sync timer. Since we already know the target system is actively utilizing gitea, let's dig into the details and see what it's up to. So what exactly is this gitea template sync service doing behind the scene while running on this timer? Looking at the configuration, it seems to be triggered a Python script named template-sync roughly every 50 seconds. Checking the file permissions, it looks like we won't have a write access unless we are the Git user. Let's take a peek at the contents anyway, shall we? With high performance, open weight LLMs pouring out left and right these days, we could easily just feed this script to an AI and ask it to find any vulnerabilities for you. But for those times when even prompting is too much of a hassle, or if you're just looking for a good brain workout, let's take a quick look at the scripts ourselves. Whichever path you choose, just remember, never let yourself skip over something you don't fully understand. That's how technical debt piles up, and keeping it unchecked is exactly what leads to failure down the road. Basically, this script is an automation tool that searches for Git repositories with the template attribute enabled, and then syncs their files to a specific directory path, staging dir /home/git/template-staging. When it comes to Python script like this, a solid approach is skim through the function names first to grab a high-level overview of the logic. From there, you want to check for any referenced external files, pay close attention to any system file path, and keep an eye out for any logical flaws or bugs in the if statement. We can see a file that seems related to Git's configuration, especially the API token. But since we already have a Git user secured, let's just bypass this for now. Right here, this is exactly where we stumble upon a highly fascinating attack vector. This code takes a file name from inside the Git repository and directly concatenates it using os.path.join without any citation. What if an attacker creates a repository in Git, names a file something like //etc/cron.d/malicious job or /home/git/.ssh/authorized keys, and then sets it as a template repository? When this timer script triggers, the // directory traversal sequences inside the file path won't be filtered out, completely escaping the staging dir. In other words, it introduces a severe arbitrary file write vulnerability, allowing an attacker to force create or overwrite files at any desired system path. If this template sync service is running in the background with root privileges, we can leverage this path traversal to inject a malicious script into directories like /etc/cron.d or /etc/sudoers.d. Once executed with root privileges, boom, instant full system compromise. So our next move is clear. All we need to do is spin up a repository containing a file with a malicious path and then marks it as a template repository. When the timer triggers, our payload will break out of the designated backup directory and plant the file exactly where we want it, executing whatever malicious code we choose. Now that we have our game plan, let's not waste any time and jump right into it. First, let's go ahead and initialize a standard empty Git repository. Next, let's write out the contents of our malicious crontab script that's going to be executed with root privileges. Next, we are going to manipulate the Git index system to first register a bad path as our file name. To truly wrap your head around how this works, we need to take a quick dive into Git Internals. On the standard Linux and Unix file systems, you strictly cannot include null bytes or directory separators like / in a file name. The OS just won't allow it. But remember, Git is essentially a database, a specialized key value store meant for managing source code. When Git manages a project, it converts everything into SHA-1 hash-based files and stuffs them inside the .git/object/directory. To understand how we are going to abuse this database, just take a look at this diagram on the screen. First, we have blobs, which hold the raw, pure contents of a file. But notice how it has absolutely no information about the file name itself. That file name metadata actually lives in the next layer, the tree, which acts like a directory structure mapping out file permissions, object types, hashes, and control names of our files. And finally, all of this gets wrapped up into a commit, which just ties that tree hash together with the author and the commit message. So here's the kicker. Inside the Git, all file contents and paths are ultimately stored as a structured text files. This means if we completely bypass standard OS commands and write our payload directly into Git's internal index, right into that tree layer, we can evade the OS file system filtering entirely. This lets us force inject a file name with raw unfiltered /sequences straight into the database. First, let's shove just the file contents into the Git database. Now we'll try to force map it into the staging area under our bad path file name. Well, it looks like we just got caught by the Git commands file name validation filter. Plan B. Instead of updating the index directly, what if we use the low-level MK3 pipeline to forge a tree object from scratch? Let's see. Alright. It seems those clever Git developers patched the local Git client to defend against exactly this kind of attack. Touché. But hey, we are not giving up here. Remember, the backend Python script running on the target server completely lacks this file name validation logic. If we just bypass the nagging of our local Git client and successfully push this into the target server, we can still pull this off. To sidestep the nagging of our local Git commands altogether, we are going to bypass the Git program entirely. Instead, we'll use a Python library called Dulwich, which allows us to manipulate the binary database inside .git in its completely raw form. In case you're wondering, the attacker's machine remains safe because it only writes data directly in the internal database without performing a checkout operation to extract the files. that's it. Today we successfully pawned the target machine by chaining together multiple attack vectors, leveraging credentials unearthed from a gitea repository history, exploiting a file upload vulnerability in Crane CRM, and pulling off a path traversal attack through the gitea template sync service. Interestingly, we didn't even have to touch the gitea CVE 2026-60004 vulnerability we discovered earlier this time around. We are going to leverage the target's gitea user credentials to launch our attack. Perfect. Let's head over to revshells.com and grab a standard batch. Actually, let's grab a BusyBox NC reverse shells payload instead and fire it off. Wonderful. We've successfully popped a shell as the Git user. Now that we are in as Git, and knowing the target system is actively running a gitea instance, why don't we take a closer look at what other services are running under this user context? Right here, we can spot yet another potential attack vector. In this location, we can harvest the password hash and salt data for gitea admin user. Let's take this recovered password hash and salt, convert the format using gitea2 hashcat.py, and try to crack it on our host machine using hashcat mode 10900. Wow, this bad boy uses the pbkdf2-hmac-sha256 algorithm with a massive iteration count of 50,000. It's definitely going to take some time, so let's jump over to our host machine where we can utilize a GPU and fire off this Nope, nada, it didn't work. But hey, we just learned a pretty useful trick, didn't we? Alright, I get it. Let's cut the chit chat and head straight over to the template sync script right away. Alright, to maximize our learning experience today, let's go ahead and patch this vulnerability ourselves. First, let's use os.test.appspath to resolve any data/structures and calculate the actual absolute target path. Next, we will check this absolute target path actually starts within our allowed stage path directory. If a dangerous file is detected, we'll just log it and skip right over it. Now that we made the modifications, we need to verify if our patch actually works, right? Let's delete the root batch file we created during our previous arc and then monitor the logs together to see if the patch holds up. Great, awesome. We have successfully patched the vulnerability. Feel so proud and rewarded, thinking that I've contributed to making a system just a little bit more secure. Hey, don't look at me like that. You've got it all wrong. This isn't malicious at all. In fact, finding and reporting as many vulnerabilities as humanly possible is the noble duty of the true penetration tester. Don't you agree? You should know that the very moment we realized we could modify a script running with full root privileges, it was already game over for this server. That's it. Today we gained initial access to the target server through a Crane CRM file upload vulnerability. Then, using the harvested credentials, we exploited CVE 2026-60004, a nasty remote code execution flow triggered by a three-way merge vulnerability during Git's patch file parsing. This allowed us to inject a malicious script directly into the repository's hooks directory, execute arbitrary commands, and ultimately hijack the root level scheduler script. By the way, now that we have two different outros for this video, I guess I'll have to merge them together at some point. Thank you for watching, take care, and I'll see you guys in the next one.